Hey guys, in this video we're going to be talking about when functions are continuous at a point x equals c. So there are going to be three requirements for a function to be continuous at x equals c. The first one is that our function is defined x equals c. So what does this look like? Well, let's say we have a little function. So let's draw our graph, and let's say it just looks something like this. And we're saying our point C is right about here. So if we look right at this point, our function is defined at x equals c. Let's say that this y value, for example, is 2. You plug in c for x, and you would get 2 for y. So our function is defined there. So we are good for that one. Next up, our second requirement is that the limit as x approaches c exists. So let's talk about when this occurs and when it might not. So we'll draw two little graphs here. In our first one, let's say we have something that looks like this, and this is a common graph you'll see. And right here is our point C, right where we have those two dots. So if we were to take our limit as x approaches c of f of x, if this is f of x, then we're approaching a different value from the left side than we are from the right side. So our limit would not exist here. So this would not be continuous. In our other graph, let's say we have something like this. So a little upside down parabola. And let's say our point C is right here, right at the origin. Okay, so right there. We're approaching the same value from the left side and from the right side. So our limit exists at this point. So we would be good. Let's talk about our third requirement. Finally, the limit as x approaches c of f of x must equal f of c. So this may seem kind of like a combination of the past two, because it has to exist at f of c and we have to have a limit as x approaches c of f of x. But they also have to be equal to each other. So let's talk about a case where this happens and a case where they're not equal to each other. So again, we'll draw our two little example graphs. Say we have upside down parabola, and let's say that this point right around its vertex, it's going to be an open circle, but then we have a closed circle down here. Okay, so notice two things. Our limit as x approaches c, if this is c right here, well, we have a limit there, right? We're approaching the same value from the left and the right. So say this is y equal to 2. Our limit as x approaches c of f of x would be 2. But our value f of c, if we plug in c, say that's like 1/2. So f of c would be equal to 1/2. So they do not equal each other. So this would not be continuous. Now, say we have the same little parabola sort of function, but there's no hole and there's no little dot to fill in. In this case, we're approaching the same value, if this is c, from the left and the right. So we have a limit, and if we plug in c, we get 2 for f of x. So in this case, our limit as x approaches c of f of x and f of c are the same value. So we're good to go. Thanks for watching. I hope this helps.